All right, so let's discuss continuity for just a second. So there's several different definitions that you can talk about, read, whatever, with continuity. And they all, pretty much mean the same thing. You've got epsilon delta definitions. You got this one here that I've got on the screen. Whatever. So continuity in a nutshell only means that you've got a couple of things that happen for a point on the function. One, the limit has to exist. Two, the function has to be defined at that point. And three, the limit has to equal the function, right? So you've got those three things. So one, the limit exists. Okay, so if you look at the limit as x approaches c of whatever that function is, it equals something. Okay. Two, okay, f of x equals something. Okay, the function has to be defined. Three, those two somethings have to be the same. And if that's true, then the function is what we call continuous. Okay? So let's look at some examples, because sometimes examples are just the easiest way to see things. So let's say that we have the function f of x equals x squared. Okay? Just as an ugly little sketch. I'm not a great artist or anything, and I'm not worried about precision here. So just general idea. So let's say we want to consider this point where x equals 2. Okay? So the first thing is we look at the limit as x approaches 2 of our function. So, okay, well, if I do that, then that's going to equal 4. Okay? It turns out, if I evaluate the function at that point, I also get 4. So, given that these two things are equal, f is continuous at x equals 2. Now, as a layman's type thing, a function that is continuous at all of its points is if you can draw the graph without picking up your pencil. So sometimes it's easier to spot discontinuities, right? If I look at f of x squared, I could trace this graph. And I never have to pick up my pencil, okay? I didn't have to pick up my pencil here when I hit x equals 2, so that tells me it was continuous at that spot. Now consider maybe if f of x equals x squared minus 4 over x plus 2. So what does this graph look like? Okay. That actually looks like straight line coming through here, and at x equals 2, or x equals negative 2, sorry, over here, we're actually going to have a little hole in the graph. So let me redraw this so it looks better. Cool. So this is when x equals negative 2. Now, if we look at this limit at negative 2, what's going to happen? What's that going to equal? So that's x squared minus 4 over x plus 2. Now we know we could go ahead and factor this and reduce things, because that's x minus 2 times x plus 2. Plus 2, when you see, oh look, the x plus 2's are going to cancel out, and now I can evaluate this function. That's going to be negative 4. So our limit is equal to negative 4. However, f of x, or f of negative 2, is not defined. Okay? Because if we try to evaluate f of negative 2, we're going to wind up with negative 2 minus 4 over negative 2 plus 2, which means we're going to get 0 over 0. That's a problem, right? Not allowed to have zeros in the denominators. So that means this is not continuous. It's discontinuous at this point because there's a jump. The limit doesn't match what the function is at that spot. I mean, the function is not even defined at that spot, right? So that's a discontinuity. Now, this one in particular is what we call a removable discontinuity. So a removable discontinuity is one where you can think of it, if there's a hole in the graph, you can plug the hole. If I stuck a point right there, then I could trace that graph and never pick up my pencil. So that would mean I could get rid of this discontinuity. I just have to add that point into my function. Okay? So if I go back and redefine this function as like a piecewise type thing, and say, well, this is what it is when x is not equal to negative 2, but my function is going to equal 4 when x does equal negative 2. So I add in that one ordered pair, okay? And that plugs the hole in the graph. That's what we mean by a removable discontinuity. We have removed the hole in the graph. We plugged it up. Okay? So if I do this, now it's continuous because the function is defined everywhere, and my function, the value of the function, actually equals the limit of the function as well, because we knew the limit was negative 4. That's how I knew to set that as my value for that piecewise. Okay? So that is a removable discontinuity. Now, the other type of discontinuities we come across are the ones that aren't renewable. Look at that dotted line. I did not try to draw a dotted line. Let's see. Maybe let's let f of x equal 1 over x squared. Okay. That graph looks like this. Excuse me. Now, the limit as x approaches 0 does not exist, right? It's equal to a positive infinity. That's just a shorthand notation, right? But it does not exist. Well, if the limit doesn't exist, we already have a discontinuity right there. Okay, because remember, it has to have a limit. It has to be defined at that point, and they have to be equal to each other at that point, the limit and the function. Okay, so we already know this has a discontinuity at x equals 0 because the limit does not exist. Now, imagine these two pieces of graph, they keep going up, 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 and they keep getting closer and closer, but you can't plug that hole because no matter where you put a point on the x-axis, it's never going to be the same as what the limit equals because, well, in this case, it's doesn't exist, so we can't put a real number in there that's going to kind of plug up a hole. You can keep imagining these keep going, further and further up, and they keep getting closer and closer to the x-axis, but they're never going to touch the x-axis. So no matter what, if I put any kind of point in there, it's never going to join those two pieces together. There's always going to be a gap. So that is not a removable discontinuity because we can't fill in that hole. Okay? Now, there are lots of different types of things that are removable and not. These are just kind of a couple of examples, but that's kind of how I think of them. A removable discontinuity just has a hole in the graph. We can plug it up. One that's not removable, there's a discontinuity there, but we can't plug the hole. Another example where it's maybe not even infinite and stuff. Let's see. Let's think about a piecewise function here. If x is less than 0, we're just going to say, well, it's equal to x. And then if x is greater than or equal to 0, let's say it's x plus 1. So this graph is going to look like that. Right? Now, the limit as x approaches 0 from the, let's say, right-hand side is going to equal 1. The limit from the left-hand side as x approaches 0 of our function is going to equal 0. Since those are different, the limit as x approaches 0 of f of x, of course, does not exist. So we have a discontinuity here. And now, it doesn't go up to infinity, and the edges don't get closer and closer to each other. But notice, no matter where you stick a point in the middle here, it won't kind of join those two pieces together. It doesn't plug that hole. It's like the hole is way too big to be plugged up. Okay? So this is not a removable discontinuity either. And there's no way to redefine and add in just a single point that would join those two pieces together. So in a nutshell, that's what you're looking for and thinking about when you're talking about a removable discontinuity versus one that's not removable. I hope this helps a little bit. If not, I'll be happy to provide some more details.